Oh, great. It's in the same stack as the graded pie. Sorry. Oh, I must have punched the button already. These are the topics we're going to cover today, but they don't mean much right now unless you've read ahead. Read the chapter ahead. Nobody's read the chapter. Okay. First time for everything. So let me back up. I accidentally punched ahead, I think. Now, so we know how to determine the molar mass of an element. Right? You just look it up. It's in the periodic table. So that's the mass of a mole. We haven't defined a mole yet, though, have we? Okay. Well, so far, those numbers, you know, the mass, the atomic number is the number of protons, right? Remember that part, okay? And then the mass number is neutrons plus protons, but the average mass, atomic mass of an element is that fractional number. It's kind of close to the mass number, but it's not exactly the same because it's a weighted average, okay? I think we covered that. Well, all right, we'll take them in order. So suppose you have a formula with more than one element in it, and you want to know for that atom combined with these two atoms, how much will it weigh? It's simple. You just total up the individual weights. If you have two of them, of course, you got to multiply by 2. So you got 2 fluorides here, and you got 110, and add them up, and that unit is 156.71 atomic mass units. Okay. So what we're saying is, with this unit of measure, you got 1 atom of 10 and 2 atoms of fluorine. That's what that means. And when you put those 3 together, you get that many atomic mass units. Okay, how about sulfuric acid? Well, we need 2 hydrogens. Okay. We need 1 sulfur, which is 32, I think. 3206. Okay, and we have 4 oxygens. Then just add them up. Okay. And you should get 98, or pretty close. We're going to have a fraction maybe rounded off, be 07. Let's see. 2, 4. 5, 6, 4, 5, 6, 7, 8. Yep, 98 atomic mass units for that sulfur, sulfuric acid. All right, now for the mole. The atomic mass units, while it's true, that formula, individual atoms, possesses that many, say, 98 atomic mass units for H2SO4. It's not very useful because I don't know of any balance that'll measure in atomic mass units. They don't exist. So we need a more convenient unit of measure. And in order to do that, on the common balance, we're weighing in grams usually. We need a whole lot of atoms. I mean, lots of atoms. Almost uncountable. And that's where this unit of measure, the mole, comes in. The mole is just a number of something. And it turns out to be an exact number that's experimentally determined, actually. 6.022, oh, there it is down at the bottom, times 10 to the 23rd things equals a mole. Okay, so it could be atoms, could have a mole of atoms. You could have a mole of those H2SO4 units. You could have a mole of water molecules. You could have a mole of chickens, for all I know. It's still that many of them. Okay. So if you have this many of something, you have a mole. And interestingly enough, if you have that many atoms of a given element, then the atomic mass units for that element equals grams for that element. Right? So if carbon is, let's see, if carbon from your table, the average atomic mass of carbon is 12 atomic mass units. That's your weighted average for carbon in the natural environment. If you have a mole of those carbon atoms, you also have 12.01 grams. So that makes calculations much easier and measurements much easier. If we weigh out that many grams of carbon, we know we have that many atoms. Well, of course, we need a standard too. And the standard is carbon. Only it's one isotope of carbon, the carbon-12 isotope, which has 6 protons and 6 neutrons. So that isotope is our standard, and it's fixed. That carbon isotope, well, we mentioned this earlier with reference to atomic mass units, right? So that's fixed at 12. Let's keep going. Atomic mass units. But if you have a mole of these, you also have 12 grams. Okay. So we're still fixed on the same standard. So notice also that if we say, they kind of got carried away here. And I mean, that's true, but it's not very useful for us. This equivalence, 1 mole equals that number of objects. Remember, anytime you have an equivalence, you have the potential for a conversion factor. So if we know we have this many objects, then we can convert that to so many moles. Or if we know we have a certain number of moles, we can convert that to an absolute number of objects using that equivalence. Okay, 1 mole of eggs contains, obviously, 6.02, should be another 2 in there, times 10 to the 23rd eggs. And this is the molar mass I was referencing before. When we say we have a mole of an element, and then we can read the mass off of the periodic table for that element. And that's known as molar mass. It's just the mass of a mole of that element. And in nature, the weighted average molar mass for nitrogen is 14.01. And you just add up the molar masses, just like we did before with atomic mass units, the molar masses of each one of these, 12.01 and 2 times 16, and you get 44.01 for carbon dioxide. So if you have a mole of molecules of carbon dioxide, then you know that mole will weigh 44.01 grams. Okay. So let's see if we know how to use this. If we want to know the mass of C2H6, and we know we have 2.5 moles, right? How are we going to find the mass? Anytime you have reference in a question to moles and mass in the same sentence, think molar mass. Grams per mole. So C2H6 would be what? It'd be 2 times 12.01, and then 6 times 1.01. I need to write larger. Okay, it's picking it up. So what would that be? Let me use my calculator. I get in trouble when I try to do it in my head. 24.02 for this one, and 6.06 for the hydrogens. So I get 30.08. Accidentally punched a button again. What did I say? 30.08?
Yes.
Okay. Yeah, you're right. Okay, what are the units on that? That's grams per mole of that formula. Okay, sometimes it's a molecule, right? If you've got covalent bonding, you have non-metal bonded together, then it's an individual molecule. In other words, it stands alone on its own. If it's a metal and a non-metal, you're going to have an ionic compound. And then this is the simplest formula ratio of the elements, right? Because ionic compounds, they're in a matrix of positive and negative ions. So they're not individual molecules. So sometimes you'll hear this referred to as molecular weight. And I often do that too. When I put it into the context of an unknown in a formula, I may say this. So that's what I mean, molecular weight, molar mass. But I use molecular weight for ionic compounds too. Just force of habit. Okay, so now we know this equivalence, that many grams per mole. We have this many moles. So now, where are we headed? We're headed toward grams, right? So grams has to be on top, right? Dimensional analysis. Remember at the very beginning, I said a lot of the problems in chemistry can be solved with conversion factors. Just convert units. So this is grams per mole, right? 1 mole is 30.08 grams. So we just multiply this times that because these two cancel. I've still got it in my calculator. Oh, messed up. And 2.5. So I get 75.2. Oops, two significant figures. 75 grams. Okay. That's off a little bit. Why did they say 07? They probably used 1 here instead. That's why this is only 07 in their calculation, unless I miscalculated. 62. No, I'm right and they're wrong. Calculate the number of moles in 50 grams of water. So now we're starting from grams and we want to find moles. So with 50 grams of water, we want to go to so many moles. By the way, the abbreviation for moles is MOL. The full name is MOLE. So they just dropped the E for an abbreviation. I never did figure that one out. Okay, so we need grams on the bottom, moles on the top, right? So we can cancel the grams. But you still have molar mass as your starting point. So what's the molar mass of water? 16 plus 2.02? 18.02. This thing's giving out on me. Okay, 1802 into 50. I get 2.77. That's how many moles of water we have if we have 50 grams. See, I got it wrong again. Did I calculate? Hold on a second. Nope, I'm right. Okay. And we don't have to be limited to small molecules. I mean, the sky's the limit. You can have, a string of elements, and some organic compounds are massive. The system still works, no matter what size the formula. In this formula, we've got aspirin, right? Everybody knows, have you ever read the chemical name for aspirin? Acetyl salicylic acid. Ever heard of that? No? Okay. That's what it is. And it was discovered about 20 or 30 years before the Bayer company decided to market it in Germany. So it's sort of a curiosity to a research chemist, and then it sort of lay around until Bayer got hold of it, turned it into a pain reliever, fever reducer. It's pretty effective too. In fact, it keeps your platelets from sticking together. Take a baby aspirin every day because my doctor tells me to. What's the mass of 1 mole of aspirin? Right. So when the question is phrased that way, you're looking for molar mass. You just need 9 times carbon, 8 times hydrogen, and 4 times oxygen. Add them together. That's the molar mass. Turns out to be 180 grams. Okay. Okay. So when we write a chemical formula, these slides are kind of out of order, I think. When we write a chemical formula, right, you already know how to name a chemical, a compound of some kind. So this is kind of redundant. These subscripts are the number of each atom. And we covered that early on. When I have my generic element, remember that? It's got 4 positions around it. This is the number of the elements. So any formula is going to tell you how many atoms there are in that formula unit. Like I said, if it's covalently bound, it's a molecule. If it's ionic, then that's the simplest whole number ratio. Right? So you can tell from this one that that's definitely not ionic, because if that's the correct formula, N2O4, we could reduce that further. We could make what we call an empirical formula, which is the simplest whole number ratio. This is the molecular formula: 2 nitrogens and 4 oxygens bound together. And if you want to know that's as far as they're going with that discussion. How many moles of carbon atoms and hydrogen atoms are present in 2.5 mole sample of ethane? All right, we did 2.5 moles of that before, didn't we? I think we did. So what is this actually saying? If we have 2.5 moles of that compound, how many moles of carbon atoms? Well, if you've got this many moles of that unit, how many moles of carbon do you have? You have 2 times that, right? This is that many moles of that whole unit. So now you have 5 moles of carbon atoms. Okay. And you have, what's 5 times 2.5? 7.5? No, 12. 12.5. So you have 5 moles of carbon, and yeah, that's right, 12.5 moles of hydrogen. Right? If we just have 1 mole, how many moles of carbon do we have? 2. And you have 5 moles of hydrogen in 1 mole. But we don't. We have 2.5 moles, 2.5 times that value. It's important to get a grasp of this concept, because we're going to need to use that when we balance equations and use those equations to say things about the reaction. We need to be able to do these calculations.
So you would multiply each individual element by the moles.
Right. However many moles of the total. is the moles of atom that is in this whole system. Okay. 15. I can't even multiply. 2.5 times 5. Is that right? Oh, I wrote the wrong number. That's right. I guess we used to call them wrong. I stumbled on my own, stepped on my own rake. Okay. In this formula, how many moles of carbon atoms, hydrogen atoms, and oxygen atoms are present? We have 9 carbons, 8 hydrogens, and 4 oxygens. 984. Yeah, there we go. Right. And that says that you have, that's based upon 1 mole of that unit. Okay. So for 1 mole of that, then you have 9 carbons, 8 hydrogens, and 4 oxygens. Okay. My guess is this calculation is how many actual atoms of each do you have. So you just have to multiply these values times Avogadro's number, which is 6.022 times 10 to the 23rd. Okay. Stop me if I'm moving too fast. Okay. If you like flow charts, there you go. I think this is out of your book. You'll probably find it in that chapter. Yeah, I like the conversion factor approach. It's more flexible because with a conversion factor approach, you say, here's what I have, here's what I need, and then you work your way to that end. Just sometimes you have to chain conversion factors together to get there. But you don't have to rely on rote memory of steps, rules to get there. I never did like that. I mean, there's a place for memorization, don't get me wrong. But when you can do it logically, I think it's more flexible. Okay. So here's some, let's see. All right. We did this one before, didn't we? When we were talking about dimensional analysis, how much money does it take to get from, how much will it cost me to drive from one place to another? Right. I think we did maybe Chicago to Los Angeles or something like that. Okay. So I'm not going to spend a lot of time on this one. I do this calculation regularly because I have family in Atlanta. So I want to know how much it's going to cost. And the one variable, since I've had the same car since 2010, the one variable there is not gas mileage, but cost of the gas. So I figure that in and say, okay, I need to be sure I've got this much money either in hand or in the bank to pay for the gas, so I can get down there and back, plus a little driving around. Actually, in Atlanta, there's a lot of driving around. I think it takes 30 minutes to drive the perimeter, I-285. It's a long way. And it's crazy. Okay, so these are the calculations you would do to find out how much it would cost. And it's just dimensional analysis, right? And this must have been a long time ago. It cost that, and it's going higher, believe me. Especially if Congress spends $3.5 trillion. Because they don't have that money. They have to print it. And any economist will tell you, if you increase the money supply, you don't increase the goods to go along with it, it costs more to buy the goods that are left. It's just simple economics, which apparently Congress doesn't understand. Which of the following is closest to the average mass of 1 atom of copper? This is kind of a stupid question. Right? Is 1 atom going to weigh that many grams? you put one atom on your balance, because we have balances that'll weigh that. Right? So you just say, no, it's got to be this one. But you can do the calculation also. I don't know if we put the calculation up there. No, we didn't. Let's do it. One atom of copper. That's where we're starting. One atom of copper. So if we want to find out what the mass is, we're headed to this one, grams. Right, somewhere over here, we're going to have grams. We got to get there. So what do we know? Sometimes it's easier to work backwards. Right, when you're thinking numbers and mass, there's molar mass. It'll just be automatic. Light bulb go on. Molar mass. So if we want to end up with grams, somewhere down the line, we've got to have grams and moles like this. That way we can get grams over here and cancel moles. Right? So what's the grams per mole for copper? 63.5. 63.55. There we go. Okay, so that gives us grams. Now we got to put moles over here and atoms here. So that moles will cancel and atoms will cancel. And this is Avogadro's number. But that's not picking it up too well. I'm writing too small. Okay, so we have this divided into that because everything else is ones. 6355 divided by 6.022 times 10 to the 23rd will give you that value. Okay. 10 to the minus 22, right? This is 23, 10 to the 23rd in the denominator, which means in the numerator, it's 10 to the minus 23rd, correct? In case your calculator messes up, what do? I mean, if you can't figure it, it's not going to do scientific notation for you automatically. You just take these two numbers, 63.55. $63.55 and divide by 6.022, right? And then that number is times 10 to the minus 23, because this is in the numerator now, correct? 10 to the 23rd in the denominator, minus 23rd in the numerator. And then whatever that value is, then simplify it, of course, turn it into, this will be in the neighborhood of 11, 10 or 11, actually 10.55 times 10 to the minus 23rd. So then you move this decimal over here and store that 10 over here, which makes this one 10 to the minus 22. Okay. It's kind of like boot camp, right? Anybody ever been to boot camp or know somebody trained in the armed forces? They teach you how to use that advanced technology, but they also teach you what to do if your technology fails, because it will. I mean, anything, once combat starts, they say, that's it. It's the fog of war is what they call it. So if something's going to fail, Murphy Code steps in and makes it fail. So you got to be prepared to go on without it, right? They can, all of our troops are trained to read maps, right? Not just use GPS, we got to read a map to find out where they are and where they're going. Well, this is similar. If your calculator fails, you can do this calculation even without your calculator, right? Longhand division, everybody remember how to do that? Okay, way back in grade school, maybe. The only one I can't remember how to do is square roots by hand. I think I could probably relearn it, but I just don't use it, so I don't remember how to do it. Okay, enough said about that. Number of copper atoms in well, this is kind of a trick question. How many copper atoms are in 63.55 grams of copper? 1 mole, right? 6.022 times 10 to the 23rd. Just checking to see if you're paying attention, I guess. Okay, now we're gonna do some comparisons. If we have 100-gram samples of each of these elements, which one contains the greatest number of atoms? Okay, if you've got 100 grams of every one, but each atom has a different mass, then which one's going to take more to get you there to 100 grams? I'm sorry?
Magnesium.
Yeah, the lightest one. That's right. Magnesium is the lightest element in that group. So that one would have the greatest number of atoms to give you the same mass. Okay. Now we complicate things. We have different masses of these, and we want to rank them in descending number of atoms. So the most number, the next most, and the least number in that order. So your inclination might be to do the calculation, just convert to how many moles it is. But there's a simpler way and a quicker way. If you're in a testing situation, you want to be fast and accurate. So 107.9 grams of silver, how many moles is that? Is that 1 mole, less than a mole, or greater than a mole? Let's say silver. 107.9, that's 1 mole. Okay, how about zinc? 65.39. You've got more than a mole, correct? Greater than a mole. How about 21 grams of magnesium? I know that one's 24.3. So that's less than a mole. Okay, so now we can put them in order. Let's see, according to descending number of atoms. And this is a unit of measure for numbers. So you don't have to calculate the numbers of atoms. That's what this says. And if we're going to rank them, that's as far as you need to go. So the most, greater than a mole. So we have zinc, greater number than, in the middle is silver, and then magnesium. Right, descending number. That should be right. Okay, I did the calculations there just to prove I can. But it should be in that order. See, B is zinc, yep. A is silver, and C. Okay. Now, sometimes you will have to do those calculations to answer questions. But there were only 3 of them here, so I figured that's the simplest way. Keep it simple. But if you have to compare a large list, you know, that simple comparison may not be enough. So then you have to do the calculations. And in that case, you channel. Anybody know what I mean by channeling? It's a term that a new age term for, you take some person that has died in the past and claim that their spirit is working through you. You're channeling that person. Okay, I'm going to channel Henry Ford, the assembly line. So you just set it up with the same type of calculation for everyone, so that you know that you're not making a mistake. You just do it the same way for each one, and you come over here and then you compare. Assembly line. Okay, 100-gram samples of each of the following. Here we go. We've got 4 compounds. Water, dinitrogen monoxide, carbon dioxide, and I'm pretty sure this is propionic acid. Descending order of number of oxygen atoms. So we've got a 100-gram sample of each one. So that means you're starting off with water, dinitrogen monoxide, propionic acid, oops, there we go, and carbon dioxide. Okay, and you have 100 grams of each one. See? It's just repetitive. Do the same thing over and over again. Okay. We need to convert these to what? Well, if we're going to have numbers of oxygen atoms, we got to find out how many molecules there are, because we're not told the mass of the oxygen. We're told the mass of the compounds. So if we find out the moles of each compound, then we can use what we know about these subscripts to tell us how many moles of oxygen that is. Okay. Let's see if we will work better. Okay, so what do we need here? To give us moles of each compound, we need to cancel grams and leave us with moles. Okay, so it's 1 mole each here. Water, we did that one earlier, that's 18.02. N2O4, let's see, that's 14 times 2 is 28.02 plus 16. 2802 plus 16. 2044. 4402. Okay. That's going to be hard to erase. How about this one? That was a little more involved. I have to use my calculator. All right, carbon again, right? 12.01. Times 3. And then 6 hydrogens is 6.06, right? And oxygens, 2 times 16. So that's 7409. Okay, carbon dioxide, 32 for the oxygen, right? 2/16, plus 12.01 for the carbons, which is what? 4401. Pretty close to this one. Okay, so that gets rid of the mass and leaves us with moles of compound. Right? That's how many moles of compound we have. Now, how many moles of oxygen atoms? Here's another situation where you're going to put them in descending order. You don't have to go all the way to the number of atoms. You don't need Avogadro's number, because moles is a unit of number measurement. So all we need to do is correct now. This is moles of compound. So you need another conversion factor. This is compound on each one. Right, so that'll cancel the moles of compound. So each one of these is compound. Right, for each one of these moles of compound, how many moles of oxygen do you have? First one is 1. Second one is 1. Third one is 2. And the fourth one is 2. So now we've got all those canceled, and we're left with moles of oxygen. So you should do that calculation, 100 divided by 18.02 times 1. 100 divided by 4402 times 1, 100 divided by 7409 times 2, and 100 divided by 4401 times 2. And just compare the numbers. Okay. In the interest of time, I'm not going to finish that. That's how you set it up. In fact, I had a teacher one time. I didn't care if you did the calculations. You set up the problem. They were all short answer questions. Set up the problem, show me how to work it, and then move on. And I'll look, see if you set it up right. I like to do the calculations though. That the devil's in the details. And the devil's in the calculations. Okay, so when we do that, oh, I should have looked at my hard copy. All these calculations have been done. So we get that many moles. Are they in the same order? Yep. So now, descending order. So the most number of oxygen atoms in 100 grams is water. Does that make sense? Why would water be the most number of oxygen atoms? Because hydrogen weighs almost nothing. So if you got 100 grams of water, it's mostly oxygen, right? Okay, so there's your order. And it's picked up on the video. So if you want to go back and look at it, it's there for the viewing. See how much blue smudge I got left on the board here. Okay. So let's see, what's this one? You have a aspirin again, number of molecules in a 0.325 gram tablet of aspirin, 325 milligrams. That's the standard aspirin tablet. Okay. And I'm not going to take time to do this one. The calculation is down here. We convert grams to moles and then moles to molecules because it did ask us how many molecules. We're not just comparing, we have to tell how many molecules. So it's 10 to the 21st power molecules in that tablet. Is that the only thing in an aspirin tablet? No, it's got other things there, carriers we call them. As if you tried to store fat, that compound's probably a liquid. Can't make a tablet out of it. So you absorb it in some material that's compatible with the body and doesn't interfere with the action of the drug. That's pharmacological technology. Okay, now I'm going to say what happens in a chemical reaction. Right? Remember, we're observing things at the macroscopic level, what we can see, what we can measure, but what's actually happening is underneath on the atomic level. This is one way of trying to connect with the atomic level, is writing a chemical equation that expresses what's happening in that reaction. And we always put the reactants on the left-hand side, the products on the right-hand side, and an arrow in between. And sometimes we'll even add information on the arrow. Like if we need to add heat to make the reaction go, we'll put a delta there, which means heat. Or we may say, maybe the reaction needs some type of catalyst. You know what a catalyst is? Something that speeds up the reaction. Right? We may say what the catalyst is. Right? Well, not in this case, but you know, platinum is a good catalyst for your exhaust system in your car. It converts unburned hydrocarbons in your exhaust into harmless compounds, elements. But other information can go here. We're not going to do that right now. We're going to focus on reactants, products. And you set it up like an equation, like a chemical equation, only we don't use an equal sign like you would in math. We use an arrow. This designates the direction of the reaction. It goes from here to here. And later on, well, I don't know if we're going to do it in this class or not, at least in general chemistry, we learn that these reactions, once you get enough product over here, they can start going backwards. And some reactions like to be over here, preferred. So their reaction doesn't go very far over here. And others like to go way far over here and just maybe a little bit go backwards. But that's another topic. For now, reactants, products with an arrow in between. Okay. So when we write one of these equations, that's why I was so emphatic about learning to write compounds correctly. If you can't write the compound correctly, you can't write the equation. Okay? And once we try to balance the equation, and that means you have the same number of atoms of each element on both sides, right? One calcium here, one calcium there, one sulfur here, one sulfur there, two hydrogens there, and one oxygen here and one oxygen there. So that means the equation is balanced. Now it's balanced in those terms because we have equal numbers of atoms of the elements on both sides, but it's also balanced in terms of mass. It satisfies Lavoisier's condition of conservation of mass. If you have the same number of elements on this side of each, same number of each element on this side as you do on that side, then the mass has to balance. The way this is written, you have one molecule of H2S. That's a covalent compound. You have one formula unit of calcium oxide, right? Metal, nonmetal. You have one molecule of water and one formula unit of calcium sulfide, which is also an ionic compound. So they can mix up, but these are formulas, say formula units. And how do we say whether we have more than one of them? We put a number in front called the coefficient. So if you put a coefficient here of 2, that means you have 2 formula units there. Or if you put a 2 over here, you have 2 formula units there. And we always use whole numbers, at least at this stage in your chemical education. We simplify to whole numbers. Okay? That's what the coefficients do. They tell you the numbers of molecules or elements. Let's see. No, we didn't have an element there. But if you have an element sitting in there, like say we're going to burn methane, right, in our Bunsen burners, the lab. Natural gas, mostly methane. Methane, then we're going to add some oxygen to it, and it's going to produce carbon dioxide and water as products. Okay? Coefficients work for elements also. Okay? And in this case, that's not balanced. You can see it may have 1 carbon here and there, 4 hydrogens there, but it's only got 2 hydrogens here, 2 oxygens here, and 3 here. So that is definitely not balanced. I'm going to show you how to balance equations in a minute, Bill. It's coming. And we do it once you write the compounds and the elements correctly in the equation. That's first. Then you can proceed to balance. If they're not written correctly in the equation to begin with, in the unbalanced equation, then it will never balance. Okay. The coefficients are there to tell you how many moles or how many molecules. It can be interpreted both ways. We could say 1 molecule of methane plus 1 molecule of oxygen element, right? Under natural conditions, I mean, room conditions, oxygen's diatomic. It's one of those diatomics that I had you memorize early on. Yields 1 mole of carbon dioxide and 1 mole of water. Well, we know that's not true because it's not balanced, but that's what the coefficients mean. It can be molecules or numbers of elements, depending on which coefficient is front of which. But it can also be interpreted as moles. You have 1 mole of that, 1 mole of that, yields 1 mole of that, 1 mole of that. It can be interpreted both ways. The more useful way is to look at it as moles, because then you have a handle on calculating the mass. If you know the moles of this one, we can calculate the mass. What mass of that one goes into the reaction? Okay. Balancing equation. This is your author's idea of balancing equations. No, maybe this is mine. No, this is the author's idea. I got a better idea. But the rules are true. When you're balancing this equation, once you've written these compounds and elements correctly, you cannot touch the subscripts. Never balance with changing the subscripts. That's taboo. You can only balance the coefficients. Okay? So, how are we going to do this? Well, let's see. I need to shift this a little bit. Let me rewrite that. I need a little bit of room over here. So methane's going to go here. That, and then I'm going to have reacted with oxygen. Notice I'm leaving a gap here for my coefficient in case I need one. And then my carbon dioxide, and then my water. There you go. Okay. The first way to learn how to balance an equation, I call it the budget method. Everybody have a budget at home? Do you work out of a budget? Yeah. Good deal. So you know what you have to work with. So let's see what we have to work with first. And for each of the elements, we just line them up down the side. Right? So how many carbons do we have on this side of the equation? We have 1. How many hydrogens? We have 4 and 2 on that side. On this side, we have 1 carbon. Okay, we have 2 hydrogens, and we have 3 oxygens. Okay. The beauty of this method is you can see instantly that it's not balanced. And by the same token, once it's balanced, once you get there, it's obvious that it's balanced because these numbers will match. Okay, so where do you start? Well, let me see. Let me look at my hard copy. I want to steal my own thunder. Where'd I do that? Here it is. I think I put a slide in here with helpful hints. Let me be sure it's here. Did I hand one out? Okay, good, good. Yeah, they're there. Okay, I'm just checking myself. Okay, so where do you start? Well, where you don't start is elements. Don't mess with those first. Why? Because if you put a coefficient in front of that, it only changes that one. And maybe that's what you need at the end. As your last step, if your last step is you're changing one of these, it's not going to be your last step, probably, because you're changing more than one element. So save the elements till last. So carbon's already good. Let's move to hydrogen. If you don't have an intuition about where to start or where to go, just start at the top. You'll eventually get there as long as these are written correctly. Hydrogens. We need 4 hydrogens over here. Right. So that changes the hydrogens and it changes the oxygens. 2 plus 2 is 4. Okay. So now we can go over here to oxygen and put a 2 in front of it. And that gives us 4 oxygens. Now it's balanced. That was an easy one. They get worse. I'll try not to give you 2 bad ones.
They absolutely do
My-
worse.
My purpose here is not to break you. It's to help you learn how to use the system. By the way, this compound is in a series called hypercarbons. Hydrocarbons. Inventive name. And they'll come as the next one up is 2 carbons, C2 and H6, ethane. Once you get to ethane and above, 3 carbons, 4 carbons, 5 carbons, when you burn it, then it's not going to behave very well. In fact, let me show you one. We'll just take ethane. Because if I use ethane, then I've got to show you one of those helpful hints. Ethane, C2H6. Now we know that's not balanced. So we have 2 carbons on this side. We have 6 hydrogens, and we have 2 oxygens. And on this side, we have 1 carbon, 2 hydrogens, and 3 oxygens. Okay. We do need to balance the carbons this time. So we put a 2 in front of this one, right? So that gives us 2 carbons, and it also says 4 oxygens plus 1 is 5 oxygens. That's 1. 5 oxygens. What do I have here? 2 hydrogens. Okay, balance the hydrogens. We need 6 hydrogens, right? So if I put a 3 here, that makes 6 hydrogens. But it also makes 4 plus 3 is 7 oxygens. Okay? Now here's the trick. We want to balance and end up with whole number coefficients, right? Eventually. But as an intermediate step, it's okay to use fractions. And that's what I'm going to do here. I need 7 oxygens on that side. But I've got this oxygen that's an even number, subscript. So if I put a 3 in front of it, that's only 6 oxygens. If I put a 4 of it, that's 8. So I got to split the difference. So how do I get 7 out of that mass? I put a fraction. 7 halves of that oxygen will give me 7 oxygens. Okay? There's your oxygen molecule. If I had 7 of them, how many oxygens would I have? 14. But if I have half of that many, I've got 7, right? So 7 halves gives me what I need here. Then, now that I've got it balanced, technically speaking, I can convert to whole numbers by getting rid of that 2. So, like any equation, any mathematical equation, you can multiply through an entire equation by one number and hadn't changed the equation, correct? The ratios are still the same. So if I multiply this whole equation through by 2, right? 2 times 7 halves is 7, correct? Okay. So if I do that, now I've got a 7 here. And that 2 is here. And a 2 times this one is 4. And 2 times this one is 6. There we go. So now we're still balanced. I've preserved the ratio, and you can check yourself. We were balanced before, so if I multiply through by the same number, 2 times everything, we should still be balanced. Right? In this case, we've got 4 carbons. 4 carbons. Hydrogens. 12 hydrogens. 12 hydrogens. 14 oxygens. 14 oxygens. 6 plus 8 is 14. So we're still balanced. That was the trick. Use a fraction. Okay, and that's in helpful hints here somewhere. Here we go. Here we go. There's a fraction. This is a different hydrocarbon, but it's the same problem. All the hydrocarbons are like that. Methane's the only one that behaves with whole numbers. The rest of them, you have to use a fraction intermediate. Okay. There's one other helpful hint that will simplify balancing equations, and that has to do with polyatomic ions. If you've got an equation with polyatomic ions in it, look to see if the polyatomics are intact from products reactants to products. If they hold themselves together through the reaction, you can treat them as a single balancing group. Now, if they're shattered in the process, then you have to treat them individually as atoms. But in this case, there's ammonium, right? That's the only place it occurs here, and it only occurs here. So we can use it as a balancing group. Or phosphate. Phosphate, okay, there it is. That's the only place it occurs. It's still intact. We can use that as a balancing group. And that really simplifies the whole process. And here's my animation for those. Here's the group that we're going to balance. Ammonium on one account and phosphate on the other account. Calciums, of course, are separate. Chlorines are separate. And then you just do your initial count. Okay, and then you decide, where do I start? Well, I'm going to start with balancing calciums. So that first step, these little red letters are just orders. So that if you see this all together in one shot, like on your printouts, then you can tell what order I did them in. If you don't have the animation available, then you can't tell what order this way. But with those little red numbers, it tells you I did this one first. There we go. And then this one second. And then this one third. Oops, went too far. There we go. And this tells us instantly that we're balanced. Okay. The thing that got me as a student in chemistry and all the way through to where I am now is that most textbooks, in fact, I haven't read any textbooks that give you a method for balancing equations. They just say, these are the conditions. You have to have the same number of elements on both sides. Right? Okay, that's good. How do you get there? Well, initially, they don't tell students how to do that. They just say balance by inspection. And I thought to myself, what the hell does that mean? It means that the authors just don't want to bother. So that's why I put this thing together. Okay, correctly balance this equation. Well, if we do, this is the simplest whole number ratio, and you can check it out, right? You can say, well, we've got 2 calciums there, 2 there, 2 oxygens, 5 carbons, and 4 plus 1 is 5. But the other ones, these are also balanced. They're just not balanced in the simplest whole number ratio. And that's what we prefer. If you can simplify the equation to a whole number ratio, that's better. That's what we prefer. Okay, which of the following is true concerning balanced equations? There could be more than one true. Let's see, the number of molecules is conserved. Think about what that says. The number of molecules, which means the coefficients. Can you add up the coefficients on the reactant side and they're equal to the coefficients on the product side? Because that's what it means, numbers of molecules. No, it's not necessarily true. So that was false. The coefficients tell you how much of each substance you have. That's kind of tricky, the wording here, how much of each. Much implies mass. Okay, and if we interpret it that way, then no, it doesn't. The coefficients tell you the number of moles or the number of molecules we have on each side. Atoms are neither created nor destroyed. Now, that's still true. Right? We haven't changed that law. Coefficients indicate the mass ratios? No. Mole ratios. Number ratios only. For the mass ratios, we need to do something called stoichiometry, which we'll get to. The sum of the coefficients on the reactant side equals the sum. Well, that's the same thing as 1. 1 and 5 are both false. They're saying it in different ways. So that was still true. Okay. The correct balance equation for the process of heating sodium bicarbonate to produce sodium carbonate, carbon dioxide, and water. This is a word problem that requires that you understand how to write the compounds from the names. That's why it was so important early on to learn how to do that. Except they're using old terminology, right? Sodium bicarbonate, what does that mean? The modern term for that is sodium hydrogen carbonate. Sodium hydrogen carbonate is a polyatomic ion. It's in that list. And it has a -1 charge. That is a +1 charge. So that and that is balanced. It's written correctly. And yields what? When you heat it, it says you get sodium carbonate. There's your carbonate polyatomic, has a 2- charge. So we need 2 of these to balance. Now we wrote that one correctly. Carbon dioxide is a type 3 compound. You just say how many there are. 1 carbon, 2 oxygens. And water, of course. Okay. So these compounds are written correctly. Now we can proceed to balance. Okay. We could use the budget. But in the interest of time, that's what you end up with. You need a 2 here, and that satisfies everything. Right, just put a 2 there, 2 sodiums. Right, we have a polyatomic here and here, but they're different. They break up in the process, so we can't use them as a balancing tool. So we have to say 2 hydrogens, 2 carbons, 1 carbon here, 1 carbon there, 6 oxygens, 3, 4, 5, 6. So we're balanced. I have my general chemistry students do this reaction. In fact, they've already done it. And determine what's left over. This is a solid. This is a solid. This is a gas. And when you heat it up, that's water vapor. Right? So you lose this and that when you heat up this compound. And what's left over? Well, they weigh it before and they weigh it after and say, okay, we lost something in here, and then we figure out what it is. Okay. Coefficients in a balanced chemical equation. Well, that's more than the same. We have 4 iron atoms and 3 oxygen molecules produce 2. What is that? Iron 3 oxide. Right? 3 times 2 minus has to be balanced with 6 plus, 6 minus, 6 plus. So 6 plus split between 2 irons is 3 plus. So the proper name for that is iron, Roman numeral 3, oxide. Okay. So if we have 4 moles of iron produce 2 moles of Fe2O3, is that true? Let's go back. Yep. 4 moles of iron will give you 2 moles of this. So now we're dipping our toes into stoichiometry. You can say this mole ratio is established for a balanced equation. 4 moles of that plus 3 moles of that yields 2 moles of that. That's chiseled in stone. And if you can say that 4 moles of iron yields 2 moles of Fe2O3, now you have a conversion factor, right? Because if you know, say you don't have 4 moles here, say you only have 2 moles. So if you're starting with 2 moles of iron, Then you have a conversion factor. Like that. 2 of these, 4 of those. There's your conversion factor. This is equal to that. This cancels that. Now we can find out how much of this we end up with. So 2 times 2 is 4, and divided by 4 is 1. So instead of 2, we end up with 1. Okay. That's where the coefficients come in handy. When you have the coefficients in a balanced equation, you have a number of possible conversion factors, depending on what you're starting with and where you want to end up. If you're starting here and you want to end up there, your conversion factor is a certain way, like this. If you're starting here, you say, how much would it take to give me that? Then you can work backwards to that using conversion factor. And it's all based upon the coefficients in a balanced equation. That's what they're saying here. Like 4 to 2 or 2 to 4, they're still equal to 1, right? Just like all conversion factors, they're equal to 1 because they're equal to each other. All right. We did this one earlier, didn't we? Right? 2746, was it? 274, I think it was this one. Yeah, it was that one. The reason I remember is because that's 7. Okay, now we're going to officially break the ice on stoichiometry. Stoichiometry is a fancy word for using a balanced chemical equation for a reaction to determine amounts of things that either go in or come out of a reaction. If you know what goes in, you can use the equation to find out what comes out. And this is in terms of mass, moles. If it's a solution, you can calculate the concentration, or you can mix them up. Stoichiometry will take care of all of those. And there's your flow chart again, which let's use it if you want to. This one actually, you know what this reminds me of? Reminds me of a dad taking a 2-year-old, teaching him how to swim. Goes to the deep end of the pool and throws him in. This sink or swim, right? That's what this one reminds me of. Solving this problem is like throwing you into the deep end of the pool. But it's really not that complicated. Methane reacts with oxygen and air to produce these two. We did that one earlier. Ammonia also reacts with oxygen and air to produce nitrogen monoxide and water. Okay, so you need your balanced equations first. That's given. There's the balanced one for methane, combustion of methane, and this one is combustion of ammonia. Right? Now, what's the question? Okay, what mass of ammonia would produce the same amount of water as 1 gram of methane? And the oxygen is excess. We don't have to worry about running out of oxygen. So what does that actually say? Well, if we start with 1 gram of methane, how much water are we going to produce? That's one equation. We can calculate that using this equation and our conversions. And then once we find out how much water is produced, how much ammonia would it take to produce the same amount of water? That's where we're going. It's actually 2 questions. So what do? Well, you start off with your balanced equation, and then you say, what are you given? Well, I'm given 1 gram of methane, right? 1 gram. Now here's another rule. I'm full of rules today. In order to go anywhere in that equation, you can't do it with mass. You got to have moles, right? Think of it as all the plus signs, all the arrows. There's a great wall there. You can't get over that wall. You can't get under it unless you're moles. I guess the analogy would be if I'm a mole, I can go under it. It'd have to be a bird or something to go over it. You can't go anywhere in that equation unless you're moles. So we have to convert that to moles first. Once we know the moles of methane, we can use the coefficients to convert to moles of water. If we know the moles of methane, then this balanced equation tells us that we can calculate the number of moles of water. Right? So that's what this does first. Okay. Here's the molar mass of methane, right? Cancel the grams and leaves us with moles. So that's how many moles of methane that we have, 1 gram. So if we've got moles of methane, how do we convert that to moles of water? We use the coefficients, 2 to 1. Okay. For every 2 moles of water, we need 1 mole of methane, right? Coefficients. So the moles of methane cancel, and that leaves us with moles of water. Okay? So to answer the next question, how much ammonia would it take to make that many moles of water? Because it says the same number of moles as the other equation. So this now becomes that part of this equation. That's how many moles of water we want as a product. Okay, how much of this do we need? So we take that value here and we convert it to ammonia. Moles of water, and the ratio is 6 moles of water, which cancels there, and 4 moles of ammonia. That gives us this answer. The question is, what mass of ammonia? Right? We know the moles of ammonia now, so we have to convert to mass, and automatically molar mass. Nitrogen plus 3 hydrogens, which is 1704 grams. Now, these are equal to each other, so you have to decide, do I want it this way or that way? You want to cancel moles of ammonia, so moles goes on bottom, mass goes on top. And that gives you 1.42 grams of ammonia. So we're saying that 1.42 grams of ammonia in this reaction gives you exactly the same amount of water as 1 gram of methane in that reaction. Okay? Is everybody swimming now? And you need to practice. Yeah, practice. Okay, before I flip the slides, I'm going to get this out of the way. Okay, another concept. What we've been talking about so far, stoichiometry, those equations and the calculations we did were assuming that we had no loss of product in the process. In other words, when we put in 1 gram of methane, we get that many moles of water. But in reality, you always lose something in the process. You could have a leak somewhere and the water could leak out, or you could have a purification step in reactions is often there, and purifying loses something in the process. You can have side reactions. In other words, we think that's the reaction that's happening, but maybe methane does something else in that process. Maybe it doesn't react with oxygen. Maybe it pyrolyzes, which is a fancy word for breaks down with heat and doesn't react with oxygen. So it won't produce the right product. So in reality, you always get less of a product than you expect. Now, the stoichiometry of the equation is 100%. Right? That's the ideal. Yield, when we calculate percent yield, that incorporates the real world. How much product can I expect to get from this reaction under these conditions? And we calculate that simply by the actual amount that you get divided by the theoretical amount. And the theoretical amount always comes from that balanced equation. The actual yield has to be given to you in this context, in a problem. So here's an example. What's the percentage yield of a product for a chemical reaction where the theoretical yield and the actual yield are respectively 5.6 and 4.5? So theoretical yield is 5.6 grams. The actual yield is 4.5. So you just divide 4.5 by 5.6, right? If you get a yield greater than 100%, which technically is possible, you need to question your calculation, because you should get something less than 100% in most cases. If you get something greater than 100%, then you've got contamination. You don't have your product all there. You have something in addition. But in this case, 4.5 grams is your output, and 5.6 is what you expected for the theoretical yield. So ratio those and you get 80%. Now, for 80% is really good, actually, for most chemical reactions. There are some that you're doing good if you get 10% or 15%. And part of the chemical engineer's job for the company is to improve that yield of a reaction without costing the company too much. Right? So as long as you can increase their profit margin, then you get to keep your job. Okay, concept question. We must be getting close to the end. Good, we got a half hour to go before I run out of time. Pennies produced prior to 1982 were composed of 95% copper. On average, these pennies weigh 3.11 grams. How many atoms of copper were present in one pre-1982 penny? I remember when that happened. Let's see, there's a term for that. It's called debasing the currency. And throughout history, governments have done that. They can't do what they want to do using an honest currency, like pure copper, pure silver, pure gold. So they start mixing in base metals with it, which are a lot cheaper, but they keep the value of the coin up. So it's like a hidden tax, debasing the currency. That's the way it was done for centuries, millennia. Ever since the invention of, and that's actually money. Pure copper is money because it has an intrinsic value. Paper is currency. It's not money because paper has no value. Right? That's the difference between currency and money. Just economics lesson for free. Okay, so let's answer the question. At 95% copper, and the total mass is 3.11 grams per coin. Okay, so we have that many grams. How many atoms of copper? Well, that's not all copper, is it? It's only 95% copper. Okay. So what does 95% mean? It means 95 grams of copper per 100 grams of coin. Right, that's what percent means, parts per 100, 95 parts per 100. Okay, so now we've actually converted to grams of copper. Now we find out, right, moles of copper, which is 60, what was it? 63.55. Bad eyes. Okay, so that's grams of copper canceled, moles of copper. Now, how many copper atoms? What do we need now? Avogadro's number, right? How many atoms in a mole? do that calculation. That's the hard part. That's the thinking part. The rest is crunching numbers. So this times that, divided by this, divided by that, will give you that means the same thing. Multiply that times 100 and that times 100, you get this back right here. Same ratio. 2.8 times 10 to the 22nd atoms of copper. They did that with silver coins too. Okay. And if you look at say, take a quarter, look at a quarter now on the edge. What do you see? See two different colored metals, don't you? They weld those metals together, the cheap one on the bottom and the expensive one on the top. Right? You can't, there's no pure silver coins anymore. At least not coming from the mint. You can find them in circulation. In fact, you go to a gold or precious metal purveyor on the internet, for instance, and they'll sell you bags of silver coins. I mean, 95% silver coins. They're not good, they're not in mint condition, but they're still silver. Okay. Oh, we got another one. A 2-liter bottle of carbonated soda has on an equivalent average 0.2 grams of glucose per 100 milliliters. Glucose is metabolized in the body according to this equation. Right? Our bodies actually burn glucose, only we do it in steps. Right? Lots of steps, so that each step produces a little bit of energy that is trapped by your body. Most of it, some of it is dissipated as heat. That's what keeps our body temperature up. And they do it in steps so that you don't burn up the person, kill the cells. If you do it like this, I mean, if you take, well, this is not the same as table sugar, sucrose instead of glucose, put it in, you can set that thing on fire. You can burn glucose, right, sucrose right there in your spoon. But our body does it step by step so it can trap that energy and not burn up the patient while it's doing it. Use the following steps and the associated equations to determine the number of grams of CO2 produced after the consumption of 10 2-liter bottles. So the balanced equation, you need to take that, balance that equation. Okay. And this will balance it. We used our budget method. Right? We need 6 oxygens combined with one of these. 6 moles of oxygen and 1 mole of glucose makes 6 moles of carbon dioxide and 6 moles of water. Okay. Then what are we given? Right. 0.2 grams of glucose per 100 milliliters of soda. Okay. Now we want to find out what? Well, there's the whole thing at once. Let's break it down. Here we convert to liters because our pop bottles are 2-liter bottles, right? And we got 10 of them. So 10 times 2 is 20. 20 liters is the total volume. Right? But we have to convert this to liters, otherwise we can't cancel it out. So that converts to liters, and then this cancels the liters. Now we know how many total grams of glucose there are. And we want to convert glucose to moles now, because now that we know the total mass of glucose, we want to find out how does that convert to CO2. So we convert glucose to moles of glucose. Then this converts moles of glucose to moles of carbon dioxide based upon the coefficients. There's 6 and there's 1. And now that we know moles of carbon dioxide, we convert it back to mass using its molar mass, 44 grams, rounded off, per mole, cancels moles of carbon dioxide, and there we have 59 grams of CO2. It's produced by consuming 10 2-liter bottles. Eventually. Okay. I think that's the last one. Usually they have 2 concept questions. Yeah, that's it. Any questions? work those problems. We'll have a review next week. If you get stuck, you got my email. Check me out. And if you're really desperate, we can set up a Zoom session. Use my private Zoom, and we can talk. I'll have my, if I do it at home, I'll have my whiteboard behind me, so I can talk with my hands. If we do it from school, then I'm kind of. Anyway, that's it for chapters 4, 5, and 6 for this exam. Next exam, the next 2 exams, we only have 2 chapters each. So actually the hard part's over with. If you know all this stuff up to this point, then the rest of it is fun. You believe that? It's a matter of opinion, right?
The density, like.
Okay, thank you. So let's end.